Hello, everyone. Welcome to the Thursday afternoon talks for the International Mission to Mars Engineering Design Project. This afternoon, we have Lee Irons. Lee is a scientist and engineer. Lee conducts scientific research with application to space physics and planetary science in the scientific theories of ecological thermodynamics, network ecology, and human sustainability. Lee is also a power systems and environmental engineer and experience in power system design and production, hazardous environment decontamination, environmental remediation, and large-scale engineering and construction projects, including some of the largest ships, floating cities on Earth's oceans. You can find podcast interviews of Lee on The Space Show and on Space 3D. And today, Lee will be talking about sustainable human mission engineering, performing conceptual design for mission failure risk mitigation by integrating ecological thermodynamics and network ecology principles using system architectural analysis, trade-off analysis, and bioregenerative technology. Welcome back, Lee. And I will allow you to share screen.
Excellent.
And you have the floor.
All right. And can you see that?
Yes.
Excellent. All righty. Okay, thank you for the introduction. I have 4 objectives for you in this presentation that we're going to try and get through. The first is for you to learn about the design process and all the tasks that need to be divided up among your team members in doing any design. The second is that you will learn about engineering tools that can be used to optimize your design. The third objective is to learn how to apply ecological thermodynamics and pan-cosmorial theory principles in your design. Recall I went over those on Monday. And the fourth is to learn about how to critique a design and defend your design from critique. The ultimate objective is to give you tools to not only help you design a mission optimized for sustainability, to reduce the risk of failure, but also teach you how to explain why your system is sustainable and why your competitors' systems might not be as sustainable. Recall from my presentation on Monday that we defined human sustainability as the degree to which an ecosystem supports human life and human enterprise under nominal and potentially abnormal human activity in the course of expected and unplanned events. This definition will be broken down into elements that will help you improve your design. These are listed on the slide. I will use the terms on this slide throughout the remaining slides to help you understand how to design for sustainability. The challenge is for you to design a ground system that will enable you to complete a mission on the surface of Mars. Toward this end, let's start to learn about some engineering tools for conceptual design work. Conceptual design is the initial part of every large engineering and design effort. During conceptual design, you do not go to the level of detail necessary to actually start building the design. You do go into enough detail to make some decisions about what will be a part of your design and what will not be a part of your design. You also begin to conceptually sketch about what the design will look like. The first tool to learn about is to identify your mission objectives and operational requirements. You must decide what your mission objectives will be. There are likely some interesting science missions you could do that you learned about from some of the other presenters or from some other sources. A mission objective might be something as simple as perform rock and substrate sampling of Utopia Basin. Another type of mission you might do is to prove out some technology that could improve human capabilities for future missions. You can have as many or as few mission objective statements as you wish. With a defined mission, you can start to define your operational requirements. Operational requirements are further action statements of a greater detail of things that must be done in order to support accomplishing the mission. The first set of operational requirements are the mission support operational requirements. These address the daily nominal activities that must be performed to support the mission. This might be something like monitor weather conditions. You should also identify mission operational requirements for abnormal mission events. These are those less frequent things that might occasionally need to be done. For example, secure sampling expedition personnel and equipment during sandstorm. The second types of operational requirements to consider are environmental control and life support related, considering this is a human mission. An example of an environmental control and life support operational requirement is provide breathable air. The third type of operational requirements are infrastructure. These are operational requirements that support all other operational requirements. An example is provide solar power. The next engineering tool and step in the process is to identify design objectives. Design objectives are both limitations that are put on the design, as well as things you could do to improve the design. A delivered mass limitation has been put on this mission, so reduced need for delivered mass is a design objective. This is because you must find yourself later in the engineering process. You might find yourself later in the engineering process exceeding this limitation with all of the operational requirements you are trying to meet. So you will need to find ways to modify your design to reduce the delivered mass you will need to use to be under this limit. As you develop the design, you should be looking for ways to reduce the amount of mass delivered from Earth that you need to accomplish a design that meets operational requirements. Reduced staffing could be another one, because the fewer humans that are required to go, the fewer life support resources will be needed, which also helps reduce delivered mass usage. Reducing human time on Mars can also reduce the need for mission resources and delivered mass. Three additional ones I would like to mention are repairability, sustainability, and survivability. Repairability is making sure you can complete a mission even with equipment failure. Sustainability is something I talked about on Monday. This is making sure you don't wear out, run out, or burn out before the mission is complete. Survivability is making sure you can survive unplanned events. With design objectives identified, you can return to your operational requirements and consider modifying them or adding to them based upon your design objectives. With a design objective to reduce use of delivered mass, you could add infrastructure operational requirements to provide in situ agriculture, to provide in situ resource utilization, provide in situ manufacturing, or provide in situ waste recycling. And of course, provide access from inside your containment to the Martian surface so that you can gather the in situ resources. With a design objective to reduce staffing, you can add infrastructure operational requirements to provide robotics. With a design objective to reduce time on location, you can add an infrastructure operational requirement to provide robotic construction and preparation for pre-human arrival setup. For repairability, you can add providing maintenance supplies and repair parts. Note that this can be done by using up some of your delivered mass for shipping maintenance supplies and repair parts, or it can be done by providing in situ manufacturing. Consider the sustainability design objective. I taught you last time about levels of sustainability. If you are going for level 1 sustainability, then you are wanting to provide in situ provisioning services for human use in order to reduce your need for delivered material from Earth. In this case, you need to establish a full basal ecosystem with augmentational sunlight provided by light-emitting diodes to plant life at 248 watts per square meter, and augmentational forced biogeochemical cycling, considering that gravity is only 1/3 of that of Earth, using pumps, fans, and fertilizers. Biogeochemical cycling would normally be taken care of by Earth level gravity that provides 95 watts per square meter on average, but you only have 1/3 of that on Mars. Area should be at least 65,100 square meters per person under Earth level air pressure, though more area might be advisable considering plants are not likely to be as functional at 1/3 Earth gravity. As a result, you are likely only going to be able to achieve level 2 sustainability at best, considering the challenge the basal ecosystem will have at self-balancing. You will be subject to production loss from blight and species extinctions, so you will need to account for this if you are intending on utilizing this basal ecosystem for resources. You could also try for level 3 sustainability with full lighting and forced biogeochemical cycling, but with less area and power provided for a basal ecosphere and agriculture. These are all considerations if you wish to provide basal ecosystem function. You don't have to do that, but that's something you can think about. For survivability, you can provide industrial accident mitigation systems such as fire suppression. You can also provide vital system safeguards for unplanned events. Safeguards are other systems that protect your vital systems or that protect your humans. An example might be safe rooms for humans to retreat to if the main atmospheric containment system is somehow lost. But perhaps you have already identified the need to provide a meteorite shield to protect your dome. But identifying that a meteorite might penetrate your dome is so predictable. So I would not call that an unplanned event. An unplanned event is some other means of atmospheric containment loss that you have not seen coming and therefore could not design for it. Something like safe rooms provides survivability for humans regardless of how atmospheric containment is lost. At this point, your design objectives might have enabled you to identify a very unique mission objective, to test a new and innovative technology or approach. It is okay to iterate at any time and modify your mission objectives. Your refined mission objective might involve testing in situ resource utilization or in situ manufacturing technologies. You could even have a mission to perform a sustainability test as identified in the Pan-Cosmario theory paper I presented to you on Monday. The next step is to identify system solutions to meet the operational requirements. Here you can see I've started to build a spreadsheet with the operational requirements so that I can then align the system solutions to the operational requirements. A system solution is an engineered system that can meet the operational requirements. By engineered solution, I'm referring to how engineers use mechanical engineering, electrical engineering, computer engineering, environmental engineering, and so on to develop a technological solution to a problem. Consider each operational requirement to be a problem you are trying to solve using technology. Try to identify at least 3 system solutions for each operational requirement. This will help later during trade-off analysis, as well as for ascendancy and reserve systems to meet sustainability design objectives. A system can be something that someone else has already designed. A system can also be a combination of multiple existing system designs that you are going to try to fit together in a hybrid design. A system might also be something that you would need to design from white paper in later design phases. But it is just a concept for now. Usually, standard engineering discipline can make any of these approaches work. Systems frequently are best identified by the special component technology that they use. So if you can identify 3 unique technologies that enable meeting an operational requirement, then you have effectively identified 3 systems. When it comes to technology that you can incorporate into these systems, avoid unproven technologies. These would be technologies that have not been designed yet and that you intend to design as part of the later design phases. This approach is more risky and therefore might be eliminated in the course of a design selection process. So be careful of using this latter approach of using unproven technology ideas, unless you intend proving such technology to be a mission objective. In general, try to apply the technology readiness level approach that NASA uses for proving technology to be ready for use in space. Technologies with higher TRL levels should score favorably in a design competition. List your systems and label them as mission systems with an M, ECLIS systems with an E, or infrastructure systems with an I. Here you can see that I added the system option labels next to the operational requirements on the spreadsheet, identifying all of the system options that I have listed out on paper for each of these operational requirements. For each system solution you have identified for each requirement, it is now time to identify the resources that are required. This is a list of all items needed to operate each system. Resources could be ready provisions for life support systems that are part of the delivered mass from Earth, so that a system does not have to be designed and built on Mars to provide these things. Resources could also be input feeds into systems that will process and refine these feeds into a product or service. A third category of resources are support supplies. A fourth category of resources is manufactured spare parts for maintenance or repair. You should plan to replace parts that are most likely to fail. For parts that you never expect to fail, but then end up failing, this is what we would call an unplanned event. These could be replaced by parts delivered from Earth with the delivered mass or that are manufactured in situ on Mars. For each system solution, it is now time to identify and quantify the performance requirements. These are the products or services that systems provide and the quantities at which they provide them, the qualities at which they provide them, and the resources they need to be able to provide them. You are in the conceptual design phase for this competition, so these things don't have to be exact. They are the things that you believe to be correct, though the information you have gathered in the short time you have, including the numbers, are just estimates. Keep in mind how accurate you turn out to be can help you in later phases of design. A thumb rule is to shoot for plus or minus 40% on your accuracy during conceptual design. I have started adding places for performance requirements to the same spreadsheet I showed you previously. The first type of performance requirement is the type that deals with resource requirements we defined on the previous slide. Resources can be produced and consumed. In the previous slide, we just identified the resources needed to operate each system. These are the consumed resources. For every consumed resource of a system, you either need another system to produce that resource, or you need to have the resource delivered from Earth as part of your delivered mass limit. On the right, I have started adding resources to the spreadsheet with each resource having a produced row P and a consumed row C. You will need to estimate the total mass of each resource that a system will consume and produce over the course of the mission. I recommend you use kilograms. There are 1,000 kilograms in a metric ton, so you have 30,000 kilograms to work with regarding delivered mass. At the top of this tabulation, put a row of shipped system mass. This is your total estimated mass of the installed system. You will likely need to pre-manufacture and ship most of the system equipment to Mars from Earth. You might be able to do in situ manufacturing for some structural pieces for environmentally controlled areas, so you would not include those mass estimates in the shipped system mass, but instead identify a separate resource of general or special structural kits that you manufacture on Mars. As I just mentioned, you can plan shipped resources from Earth as kits. This means you don't need to spend time figuring out everything exactly that will be in a kit during conceptual design. Just estimate the mass for the kit. So you could have a kit of all the seeds you would use for an agricultural system without having to identify every single seed type that you're going to have yet. Finally, we have performance requirements of power, staffing levels, installed area footprint, and environmentally controlled conditions. Power can be produced by a system and consumed by a system. Some of your operation requirements involve systems that produce power. Keep in mind, such systems consume power as well in order to produce power. Others of your operation requirements involve systems that only consume power. For each of your systems, identify the number of watts the system provides, if any, and the number of watts it consumes. Another performance requirement considers staffing levels. As with power, a system can support staffing levels and require staffing levels. Your ECLIS system supports staffing levels, but as with power supply systems, they can also require staffing levels. Required staffing levels are the effort required by the mission staff to operate and maintain the system. I recommend you estimate these numbers in person missions. Next, we get to the installed area footprint and environmentally controlled conditions. As with power and staffing levels, a system can support installed area footprints and require installed area footprints. We are calling systems that support installed area footprints by the term environmentally controlled area. Each separate environmentally controlled area system that you need to meet operational requirements will be based upon the environmentally controlled conditions that all of your other systems require. This gets us to the environmentally controlled conditions performance requirements, which are the conditions of the environment that the system must operate within. I have listed a number of them on the slide here. A big condition to consider is your design objective of survivability. Does a space need fire suppression? Is it a safe room for unplanned event disasters? In the spreadsheet on the right, you can see that I've identified environmental conditions sets. These are combinations of environmental conditions that are needed by groups of systems. Based upon the environmental controlled conditions that each of your systems needs, you can begin to group these by environmental condition sets that you define here. System options to consider for environmentally controlled areas can include above ground and below ground spaces. A couple of meters of regolith overhead could help you achieve some environmentally controlled conditions better than building a structure from delivered or in situ materials. As you progress, you should be including a table in a spreadsheet to collect all of this information. It can look something like this. All of the operational requirements and their system options are listed along the top. Notice that there's also a system multiplier row. I will tell you later what to do with that row. The performance requirements are listed down the left side. For each system option, you will put the power produced for power systems in the P row and the power consumed in the C row. Power numbers are in terms of watts. You will also put the staffing levels supported in the S row and the staffing level required in the R row. Staffing level numbers are in terms of personations. For environmentally controlled areas, you will put the area supported in the S row if it's a system that is an environmentally controlled area system, and the area required in the R row of the applicable environmental condition set, if it's any other system that requires the use of area. Area numbers are in square meters. Finally, for each system option, you will need to put the ship's system mass in the red D row. D stands for delivered mass. You will then put the resource produced in the P row of each applicable resource and the resource consumed in the C row of each applicable resource. Resource numbers are in kilograms. Notice that there is also a D row for each resource. I will tell you what to do with that shortly. Now that you have tabulated your system options to meet your operational requirements and all of their performance requirements, let's look at the architectural analysis tool. Architectural analysis is the next engineering tool you can use to help you understand and improve your design. Based on the resources that systems are consuming and producing, use an architectural analysis to make connections between systems such that every performance requirement of every system is being met by delivered mass or by another system you are providing on Mars. Here's an example of a conceptual architectural analysis. The arrows show the flow of consumption and production. The boxes represent environmentally controlled areas that contain groups of systems that are doing the consuming and producing. In this example, the brown boxes are what we might call people and life spaces for plants and things like that. The blue boxes are industrial areas for manufacturing and storage. The red box is a power generating area. The brown boxes follow a conceptual architecture that was patented by Morgan Irons, who presented this last Monday. This patent concept has other ideas for sustainability that you might be able to incorporate, such as three-zone system, expedited primary succession, competitive redundancy, and ecological service reservoirs. The US patent number is given on the slide as well as a link to that patent if you'd like to look that up and read about it. Have fun with the architectural analysis effort. You can start with something called a rich picture before you move on to an architectural analysis that I showed you in the last slide. You have maybe seen these on YouTube. Once you have a rich picture, you can start to do something that looks more like the previous slide. The architectural analysis will help you utilize the table you have built on a spreadsheet. The table is what we call a trade-off analysis table. For each operational requirement, look at the performance requirements of the system options and compare them to each other. You should see that each system option has its own pluses and its own minuses. What you are looking for is what you might call bang for the buck. The best systems have high production numbers and low consumption numbers. They also have low staffing levels required numbers and low environmentally controlled area required numbers. But no system option is ideal in all cases. Each system will have those things it performs well at and those things it does not perform so well at. Using these comparisons, you will first need to select what you feel to be the best system option for each operational requirement. Put a number 1 in the system multiplier row below the selected system option for each operational requirement. The system multiplier row is that brown row just below the system identifiers. Next, let's consider the sustainability design objectives. For sustainability, an important aspect to prevent is to prevent burnout. Recall from my presentation on Monday that burnout is when a system fails even though there is plenty of power available to run it. The goal is to set up an organization of systems to support each of the most vital operational requirements. You do this by considering network vitality and functional diversity. For sustainable network vitality, consider selecting 2 or 3 independent system options per operational requirement to handle 60% of the production for that operational requirement. That would be 40% nominally with 20% surge load capability. The selection can be one of the system options you did not select during your down selection process when you did the comparisons. It could also be the same system option, but simply be a redundant system. If you wish to have 1 or 2 redundant systems with the main system you have already selected, change the number 1 in the system multiplier row to an A2 or an A3. The letter A stands for ascendancy. This is the network vitality that we're flagging it as supporting. If you wish to use one of the other system options for network vitality, put an A1 or A2 in its system multiplier row. All of the system options that still have a number 1, change them to A1. These are all your non-vital systems. The system multiplier cells should add up to be 2 or 3 for vital operational requirements and 1 for non-vital operational requirements. For sustainable functional diversity, consider selecting 3 or more independent reserve system options for vital operational requirements to handle 60% of the load, 60% nominally, or 80% of the load, 60% nominally with a 20% surge load capability. The selection should be 1 or 2 system options you have not selected yet. This ensures that the network vitality systems and the functional diversity systems have different failure modes, which helps with sustainability. If you feel you need to do more research to add more system options to some of your operational requirements, you can do so at any time. Place an R1, R2, R3, or greater in the system multiplier row below each option selected for functional diversity. The R stands for reserve. The system multiplier cells for R should add up to be 3 or greater for vital operational requirements. Non-vital operational requirements do not need any R values. Next, we are going to sum up all of the performance numbers for power, staffing, environmentally controlled conditions, and resources. This is done by multiplying each performance number below each selected option by the number in the system multiplier cell, and then adding up all of those multiplied numbers in each row, placing the number, some number, in the bold box next to the column with the P's, C's, S's, and R's. Some things to keep in mind if you're providing a full basal ecosystem: make sure it has at least 60,500 square meters per person, in keeping with the Pan-Cosmorio theory. It is okay to be less than this if you are not trying to accomplish a full basal ecosystem as part of your operational requirements. Also, make sure the power to support your basal ecosystem is correct. This equation will help you do that. For Mars, the solar distance ratio is about 1.5. Your objective is for the value you calculate on the right side of the equation to be greater than or equal to 1.5. The closer you are to 1.5, the less overproduction of power you are doing. The right side should not be more than 40% greater than 1.5 for conceptual design. We are going to sum up all of the performance numbers for power, staffing, and environmentally controlled conditions and resources. This is done by multiplying each performance number below each selected system option by the number in the system multiplier cell, and then adding up all of those multiplier numbers in each row, all those multiplied numbers in each row, placing the sum number in the bold box next to the column with the P's, C's, and R's. P's, C's, S's, and R's. Now the fun begins. For every C quantity of a resource for which there is a lower P quantity, you either need to increase the system multiplier of another system to provide the needed additional P quantity sum, or you need to add new operational requirements for additional in situ resource utilization, in situ manufacturing, or waste recycling, and identify some system options to provide those additional p-value sums. Put a D quantity in the delivered mass column bolded box below the C if you cannot come up with enough p-value to meet your C value. The sum of the delivered masses in the red bolded cells cannot exceed 30,000 kilograms. For conceptual design, the sum should be within plus or minus 40% of the delivered mass limit. Once C is within plus or minus 40% of P plus D for every resource in your table, you are balanced enough for conceptual design. The closer these numbers are, the better. Remember that if you modify system multipliers, you need to recalculate the sums for all of your performance requirements. So remember, you're looking for C to be equal to P plus D within plus or minus 40% for every resource. Next, you want the number in the S sum bolded cell of staffing levels to be within plus or minus 40% of the number in the R sum bolded cell for conceptual design purposes. Getting these numbers to be as close as possible is good. If it's not, you will need to increase the system multiplier numbers of your selected ECLIS system options until the supported number equals the required number within plus or minus 40%. Remember that if you modify ECLIS system multipliers, you need to recalculate the sums for all the performance requirements. This could unbalance your resource numbers and cause you to have to rebalance them. Follow this same process to get your power produced number in the P sum bolded cell to be equal to the C sum bolded cell within plus or minus 40%. You are now at the point where you need to continue to tweak the numbers until everything is balanced within plus or minus 40% for conceptual design, but at any rate, as close as possible. The last tool I will show you is the design arrangement analysis. This is where you conceptualize the layout of the architecture with all of the systems. The simplified examples I am showing you here are from the patent I previously mentioned. You could find other ideas online or develop your own. Things to consider for your design arrangement. Draw a two-dimensional layout. If multiple levels are used, draw a separate layout for each level. Consider the total area footprints of the environmentally controlled areas. You can have each type of environmentally controlled area in a single contiguous space, or you can break it up and spread it out. For environmentally controlled areas that house vital systems, breaking them up and spreading them out helps with survivability, one of the design objectives. For systems that are connected according to your architectural analysis, but are in different environmentally controlled areas, the closer the environmentally controlled areas are to each other, the less piping and electrical and communications conduit and other materials you need to connect them, which will help you with it, stay within your total system mass estimates. Consider industrial accidents that could happen and the proximity of vital systems to places where industrial accidents could occur. Put some space between such areas to help with survivability. This is called using distance as a safeguard. Consider putting the ascendant systems for an operational requirement in a separate location than the reserve systems. This also helps with both sustainability and survivability. There are many other things to consider, Hopefully the advisors and coaches that you will have will give you some ideas and tips that you can use for your design arrangement. Now we get to the final part, critiques. How do you rebut other people's critiques of your system? Show how thorough your operational requirements are and how you will not discover once at Mars that you did not plan for some operational need, like food. Got to make sure you have food. Show how you identified and met your design objectives, such as delivered mass limitations, reduced staffing, reduced time on location, repairability, sustainability, and survivability, as well as any other special design objectives you identified. Show how you have designed the system to not wear out, run out of power, or burn out, and how it is protected from unplanned events. Show how your architectural analysis helped you meet the design objectives and helped you refine your operational requirements. Show how your system selections and trade-offs put you within plus or minus 40% of all your performance requirements. This means that your plans are balanced. Explain how these numbers are conceptual design numbers and will be refined to eliminate shortages and overages as you proceed through to detailed design. Show how your design arrangement takes into consideration the various different environmentally controlled areas, proximity of interconnected systems, and survivability against industrial accidents and unplanned events. To critique other teams' designs, show how they don't do any of these things or some of these things. Show how the performance of their systems are unbalanced or are not conceptually demonstrated to be balanceable. Show how they fail to identify vital systems and provide sufficient network vitality or redundancy, or sufficient functional diversity, which would be sufficient backup of reserve systems for vital systems. Finally, you can show how their design arrangement lacks the finesse of differentiating environmentally controlled areas, proximity of interconnected systems, and survivability against industrial accidents and unplanned events. I know this might have felt for some like trying to drink from a fire hose. You might not do all of these things, but that's okay. Have fun and do what you can. Just remember that you have a team with team members. Divide up this work amongst all of you and work together to complete these tasks. Trust each other to get the work done, and then help each other to refine your individual results to improve the result of the team. All right, that's the talk. Question time.
Thank you so much. That was so informative and helpful, helping the students structure how they're going to do things. Wonderful. Question, can you talk about the importance of in situ resource utilization of water and minerals and the regolith for a human mission to Mars?
Right, so in situ resource utilization of water is really important. And that's because water is relatively heavy and difficult to ship because it's also bulky. So, but by bulky, I mean it sloshes around, right? Trying to stick a big tank of water on a rocket and bring it with its tendency to slosh or to freeze and expand and all this, it becomes really difficult to manage shipping that from Earth. So getting water on Mars is important from that perspective. The same with minerals. If you can actually have operational requirements to refine in situ minerals into metals like refined iron and copper and things like that, if those are available on Mars, that would be ideal, because those things are very heavy and would take up a lot of your delivered mass limitation. But of course, the ability to refine minerals can be kind of difficult because you have to get up to really high temperatures to do that, which requires a lot of power. So then if you're talking a lot of power, then you're talking about having to have a lot of other solar panels, which increases your need for delivered material from Earth or for in situ manufacturing of solar panels. So you can begin to see how things begin to trade off back and forth as you look at, do we deliver it from Earth or do we use in situ materials and in situ manufacturing? But I would say water and minerals are a key thing to consider for in situ use, yes.
Awesome. What types of redundancy is needed for the ecological safety of a human mission to Mars?
Right. So ecological safety, that could be considered to be either sustainability or survivability.
Let's start with
So
survivability for the initial mission.
right. So survivability is interesting because there's a potential problem with using bioregenerative technologies in your systems. So let's say you have a system for providing oxygen to your mission, and it uses algae to generate the oxygen. And so you have a main line, an A1 line for your ascendancy for generating oxygen using algae, and you have an A2 line that uses the same technology with algae in it for your ascendancy. So you have a main line and a redundant line. Well, if there's some kind of alien vector that comes through, some kind of alien virus or bacteria or chemical or something that comes through, and it wipes out the algae in your main line, well, you're like, oh, great, main line's down, bring the redundant line up. And then shortly thereafter, all the algae in your redundant line dies too, because the same alien vector attacked both. Well, now you're dead in the water, right? So that is not a survivable situation. So that's why we say, it's not survivable, because oxygen generation is a vital system. Humans need to breathe, right? So that's why we say you can use reserve systems that have different, that are different. They have different functional operations that maybe don't use algae. They use some other method of oxygen generation to generate oxygen, so that if you have that problem, then now you're survivable because you have a reserve system to cover your oxygen, so you can figure out what went wrong with your ascendancy systems. That covers both survivability and sustainability, by the way. So sustainability is have 2 or 3 ascendant systems and have 3 or more reserve systems. We talked about that. Whereas the survivability aspect is you have no idea what could kill your bioregenerative components of your system. So you got to be very careful at using common bioregenerative components everywhere, because if it dies in one place, it's going to die everywhere. Did I answer that question?
Yes. Yeah. And last question, briefly, for the sake of time, what do you think are the top 3 most important items we need to take for human sustainability on Mars? Like, if we're going to be there for a long time, not just a visit, but forever, what are the top 3 most important items to sustain the ecological health?
Right. So seeds, because you're going to try, and you need lots and lots and lots and lots of species of lots of different things to grow plants, because you want to try and establish a basal ecosystem there. And the reason why you need lots is because you're performing an experiment. You're going to plant all this stuff in a wilderness kind of scenario and try and set up a functioning ecosystem, and then it's going to evolve because it's an alien environment. It's 1/3 Earth gravity. It's less than half the solar insolation level. And the stuff is not going to continue to be the way it is on Earth. It's going to either evolve and survive, or it's going to die. So you need lots of different species of lots of different seeds, so that hopefully some will survive when others die. So seeds is the big deal. Another thing is making sure that you can get the biogeochemical cycles going. So make sure you bring enough technology to set up a balanced sustainability basal ecosystem, so that your power, so that your dissipative structures, so those are those cycles, those biogeochemical cycles, and whether those water cycles and all those kinds of things, so that you have technology to force those things to work, because they're not going to work as well as they do on Earth, because again, there's less gravity and less solar insolation. So you want to bring enough technology with you to bootstrap that system into forced cycling, to give you enough time to get all your plants planted and things growing, so that the life takes hold and roots itself in. And once you're at that point, then the life systems can support your augmentational systems, your technology that you need to be able to repair and maintain all of your forced cycle systems, so that you can keep yourself in a closed loop economy. The important for a closed loop economy that is sustainable and long lasting in space is for at least part of your basal ecosystem to be truly self-restoring. And that's why you need to get to the point where the plant life takes root and takes hold and takes off.
Wonderful. Thank you so.
Sorry, that wasn't short.
No, it's fine, because it's important. These students have a lot to consider when they're making their project, and being able to have the fact that you said a variety of a lot of seeds is so very important. You know, astrobiology is my specialty, so I'm always thinking about that, because in human ecosystems, or in Earth ecosystems, we have to have variety. It's what makes them healthy. And so I love that was your top answer. So very important, students. So remember that if you're watching live or on the replay. Lee, thank you for giving 2 talks, and thank you to Morgan, of course. She was wonderful, as you know, and this will be uploaded within the next day or 2. Our webmaster is kind of out of service right now, so give him a couple days to get back in the swing of things. We got a lot of stuff going on.
Oh yeah.
So thank you very much, and look for the upload in a couple of days. And students, get with your teams, get started, and email me with any questions. Thank you again, Lee. Much, much appreciated. Bye, everyone.